Good morning to everybody. In this video, I am going to explain about the drift current. There are two types of currents present in the semiconductor materials. One is drift current and another one is diffusion current. The current due to the flow of applied electric field is known as drift current. That is, external energy is applied to the semiconductor material. Then holes in the p-type material is attracted towards the negative terminal of the battery and electrons in p-type n-type attracted to the positive terminal of the battery. Or in a semiconductor, in an intrinsic semiconductor, measured both electrons and holes are equal. So here the electrons are moved towards the positive terminal of the battery and holes moves towards the negative terminal of the battery. So due to the flow of these electrons and holes, there is a current flow in the semiconductor. That current is known as drift current. Due to applied electric field, the average velocity is established in the semiconductor material. That velocity is known as drift velocity. So the drift velocity due to electrons is given by Vn equal to mu n into E. The drift velocity due to holes is given by Vp equal to mu p into E, where mu n is the mobility of the electrons and mu p is the mobility of the holes. Here E is the applied electric field. The drift current density due to free holes is given by, that means movement of the holes from the valence band to the conduction band is given by Jn equal to E into N into mu n into E. And the drift current density due to holes is given by Jp equal to E into P into mu n into mu p into E. Then the total drift current density is given by J equal to drift current density due to electrons and drift current density due to holes. We know the equations for drift current density of holes and drift current density of electrons. Substitute that values in the equation, then you will get J equal to E into N into mu N into E plus E into P into mu P into E. Now take the E and small e and capital E common, then you will get J equal to E into capital E into N into mu N plus P into mu P into E. Here E is the capital E is the applied electric field. Another current is diffusion current. Here the diffusion current is only due to the concentration gradient of the charge carriers. That means here we look at the figure. Here in the first figure, the concentration of the electrons is non-uniform. In the given semiconductor material, the concentration of the electrons is non-uniform. In the second, if you observe in second figure, here the concentration of electrons is uniform. Here the electrons moves from the higher concentration to lower concentration. In the first figure. In the second figure, after the moving of the electrons, this is the second figure. In this, what happened in these figures? Here the electrons moves from the higher concentration to lower concentration. So here the movement of electrons, here the current flow is movement of electrons. So here the electrons moves from the higher concentration to lower concentration. So here drift current is said to be movement of electrons from the higher concentration to lower concentration. It's known as the diffusion current. This is another diagram for the diffusion current. Here this is for the n-type material. Here the electrons has higher concentration at the left side and lower concentration at the right side. These electrons in the higher concentration moves towards the electrons towards the lower concentration in the given area. The area is represented with A. Here the concentration P naught of x is decreases with the distances. Here at the starting the concentration is higher, but if you are going the distance is increasing, the concentration is decreasing in the second figure. So diffusion current occurs without any electric field. If you observe, we are not applying any electric field to the for diffusion current. Diffusion current does not occur in a semiconductor. It occurs only in the semiconductor material. The direction of diffusion current is same or opposite to that of drift current. The diffusion current density is directly proportional to the concentration gradient of the charge carriers. If the charge carriers is high, diffusion current is high. If the charge carriers concentration of the charge carriers is low, the diffusion current is low. So concentration gradient, here the concentration gradient is the difference in the concentration of electrons or holes in a given particular area. It depends, the concentration of the electrons is diffusion current depends upon the material of the semiconductor, type of the charge carriers present, that means either electrons or holes present, and it depends also on the concentration gradient of the material. Hall effect. When a magnetic field is applied to a current carrying conductor in a direction perpendicular to, look at the figure first. So here a magnetic field is applied to a direction perpendicular to the flow of the current carrying conductor. So here there is an electric current flow due to the holes and electrons, and there will be a potential difference occurs in the current carrying conductor. The potential. So if you apply any magnetic field to a current carrying conductor, there will be a potential. There is a potential difference occurs across the perpendicular to the magnetic field. Current flows in the current carrying conductor. So here the voltage or electric field produced due to the application of electric field. This voltage is known as the Hall voltage or Hall field. So this is the Hall effect. What is the application of Hall effect is to find, we know according to the classification of materials or semiconductors, we know semiconductor materials have p-type semiconductor material has majority charge carriers are holes and minority charge carriers are electrons. And in n-type semiconductor, majority charge carriers are electrons and minority charge carriers are holes. We know what is p-type semiconductor material and what is n-type semiconductor material, but we can't find out this one is p-type material and this one is n-type material because the charge carriers are very small. We can't unable to see the charge carriers, that is electrons or holes. So we can't say this type. While seeing this type is p-type semiconductor material and this type is n-type semiconductor material. So for that we are using to find the semiconductor material which is for p-type material and which is n-type material, we are using Hall effect. So the main application of Hall effect is to find the type of semiconductor materials. It is either p-type or n-type. So to find out the p-type semiconductor, n-type semiconductor material, here the majority charge carriers are electrons and minority charge carriers are holes. After applying the magnetic field perpendicular to the electric field direction, so here the majority charge carriers, that is here majority charge carriers are electrons. So it has this is the diagram for the Hall effect. Here we are applying magnetic field perpendicular to the current carrying conductor, then there is a voltage drop across the voltage developed across the current carrying conductor and current flows through the device. So here to find out n-type semiconductor material, the diagram in the n-type semiconductor material, it has two surfaces. One is upper surface and another one is bottom or lower surface. In n-type semiconductor material, electrons, and that means negative charge carriers, are pushed down, that means towards the bottom surface of the conductor. So maximum electrons, here we are neglecting minority charge carriers, that is holes. So here we are the maximum electrons, negative charge carriers moves towards the bottom of the surface. So negative charge is negative charge is the negative voltage is developed across the applied current carrying conductor. So this magnetic field, here the voltage, Hall voltage developed is negative. So depending on the negative Hall voltage, if it is negative, the semiconductor material is negative n-type semiconductor material. For find out the p-type semiconductor material, here also we have upper surface of the conductor and lower surface of the conductor. Here in p-type semiconductor material, we know majority charge carriers are holes and minority charge carriers are electrons. In p-type semiconductor material, we are neglecting electrons, so we are considering holes. The holes are pushed down towards the bottom surface of the conductor. So after pushing down, maximum or more number of the holes reaches to the bottom surface of the conductor. Due to this, there is a Hall voltage is developed. That Hall voltage is positive Hall voltage. That is, there is a voltage drop across the current carrying conductor. That voltage is positive voltage, because at the bottom surface, the current carrying at the bottom surface, it has a negative charge, positive charge. So developed Hall voltage is negative. So depending on the developed voltage, Hall voltage, we can say it is p-type or n-type. This is the equation for the Hall voltage VH. This is the equation for the Hall voltage VH equal to I into B by Q into N into D. Where I is the current and B is the magnetic field, applied magnetic field, and Q is the charge, and N is the number of electrons, number of charge carriers, and D is the distance or area of the current carrying material. Extreme conditions, QE equal to B into Q into VD. The electric field intensity due to Hall effect is given by E equal to VH divided by D. The current density J is related to the charge density. So J equal to current density J equal to P rho into VD. Further, the current density is related to the current by J equal to I by area. So here area is I by WD. Combining the above equations, we will get VH equal to E into D, that equal to B into VD into D. Here E equal to B into VD. So after substituting the values, VH equal to B into JD by rho. Here VH equal to BI by P into W. The Hall coefficient RH is defined by RH equal to 1 by rho. So that VH equal to RH into BI by W, where RH is the Hall coefficient and VH is the Hall voltage, P is the applied magnetic field, I is the current, and W is the width of the current carrying conductor. Applications of the Hall effect. To find whether a semiconductor is p-type or n-type, we are using all of it. And to determine the carrier concentration, how much of carriers are free electrons or holes present, it is determined by the Hall effect. To calculate the mobility of the p-type material or n-type material, that means mobility of the electrons and holes by you measuring conductivity. So the relation between conductivity and mobility is given by sigma equal to, here sigma is the conductivity, sigma equal to rho into mu, or mu equal to rho into RH. We know rho equal to 1 by RH. Mobility for n-type semiconductor material is mu n equal to sigma by n into q, or mu n equal to sigma into RH. For mobility for p-type semiconductor materials is mu p equal to sigma by p into q, that equal to sigma RH. We know here sigma is the conductivity and p is the number of holes and n is the number of electrons and q is the charge and RH is the coefficient, Hall coefficient. Thank you.